to know what it's about. Hope we find out now.
Okay.
Go ahead.
Thank you very much. Actually, today we just had a quick discussion with Professor Dempsey, and he was just saying what is peridynamics, and I'm hoping that today I will try to explain what it's all about. And I just want to make it clear that I'm not an expert on ice mechanics. Okay, so basically, in this particular study, we are just trying to show how we can use peridynamics for ice fracture. So I think it's a very nice opportunity also for me to learn more about the details of ice mechanics so that we can improve our studies on this. Before I start, basically I just want to acknowledge my kind of co-authors, Mr. Bojovazic and Juji. They are my PhD students, and Dr. Erkan Oterkus is an assistant professor in our department. And we are basically located in Glasgow. So just a brief outline of my talk. I will just briefly explain our motivation of this study, and then I will try to, as I said, try to explain what peridynamics is all about. And I will share with you some of our preliminary results using peridynamics on ice modeling. And finally, I will finish my talk with final remarks. So, I'm currently working in naval architecture, ocean and marine engineering department, and for us, it's basically, ship design is very important now. People are considering to use North Sea for the new ship route, but if that is the case, then when we design ships, we need to take into account the possible ship-ice interactions when we do our designing process. And also, of course, another important area for us is the oil and gas sector, and basically the ice interaction with the offshore structures. So when they interact, they can cause ice-induced vibrations, and ice-induced vibrations can cause certain problems, including fatigue and so on. Again, something that we need to take into account during the design process. Honestly, I'm pretty new to this field, and most of the people actually, I believe that when they think about ice, they probably think that it's a very simple material by itself. But as you see, it's a very complex material because it just depends on many different factors that we need to take into account. And also, when we look at the fracture point of view, again, depending on different factors, the fracture pattern of ice changes. So, depending on the velocity of the structure hitting ice or the size of the ice, we can observe either a ductile fracture pattern or a brittle fracture pattern. So again, what we are seeing is a very complex situation that we need to take into account when we make, or if we want to make accurate predictions. This is kind of actually a figure that I found some time ago, which was given in this particular study, and I pretty much liked it. And this is kind of what we would like to reach at the end of our studies, basically. So what we would like to do is basically we want to kind of come up with a multi-scale type of model. So when we start reaching close to the ice structure interaction place, we would like to have a detailed model, and this detailed model can be represented by using a viscoelastic material model by itself, and also it can also take into account even multi-scale aspects, so we can try to look at micro cracking happening and so on. And outside, once we go outside of this interaction region, actually we can use simplified models, and we can couple these two things together. And to obtain such a kind of a scenario, basically you would like to use a new numerical technique which is called peridynamics. So next, as I mentioned to you earlier, I will give you some information about what this peridynamics is all about. So So peridynamics is basically a new continuum mechanics formulation. Why it is new? Because we are using a different set of equations. So we are using integral equations as opposed to partial differential equations that we normally use in classical continuum mechanics. And these equations, as you will see, they don't include any type of derivatives. So it means that, if you think about fracture and cracks, we have discontinuities. So in this particular formulation, since we don't have any derivative, our equations, they are always valid. And also in our equations, as you will see, we are using very simple crack laws, which is very much simpler than what people are using trying to predict damage. And this again gives a pretty good advantage when we again predict damage inside the structures. And when we do our solutions, basically we don't treat cracks as special objects. They are just part of the formulation. So what happens is, we can have as many cracks as we have. And also it is pretty simple to take into account the interfaces. So if we have multiple materials and so on, so we can specify different properties to the interfaces. And as you will see, this particular formulation, when we discretize our system, it has the same equations, or it has the same set of equations as the molecular dynamics, although this is a continuum mechanics formulation. So we are hoping that this formulation can be used as a multi-scale tool so that we can couple molecular dynamics and continuum mechanics and so on. So before I go into the details of peridynamics, I just want to start from basics. So it will be easier for me to explain the concept. At the end, when we talk about continuum mechanics, this is a tool that we are using to try to find out the deformations, and then later on how the structures can be damaged and so on. So probably the ideal way of doing this type of studies is just to do or to perform an atomistic simulation. But as we know, the atoms are very small, and distance between atoms, they are very small. So unfortunately, with the current computer technology, we cannot model large-scale structures by using atomistic simulations. Then what do? We need to do an approximation. And the name of the approximation is called continuum mechanics. So according to the continuum mechanics, what we are assuming is each structure is made of small volumes that we call a material point. And as you see, as opposed to molecular dynamics, these guys, they are just touching each other. So there is no gap in between them. So that's why we call this as a continuum by itself. And there are different type of continuum formulations, and the most common one was proposed by Cauchy 200 years ago or so. But the continuum concept is the same. The only difference is how to define the interaction between material points. According to Cauchy, he just assumed that each material point is only interacting with the ones which is in nearest neighborhood, and also he defines this interaction as by using a contact vector that he calls a traction vector. So if you use several physics laws, like including global balance of linear momentum, then we can obtain our equation of motion. And also to obtain our equation of motion, what he basically did is he just expressed the traction vector in terms of something that he introduced as stress tensor. So now we have an equation of motion. So if we can solve this equation of motion, we can find out the motion of each material point, and it will again give us all the information that we need. And this is a beautiful equation, like things like finite element analysis and so on. We are trying to solve this equation, but this equation has a little problem. The problem is coming from the second term, and as you will see, this term has a derivative, special derivative in there, and whenever we have discontinuities like in cracks, then we cannot calculate this term. Then what happens is, we need to use some other techniques, like linear elastic fracture mechanics, and as we saw earlier, quasi-zone model and so on. But instead, if the problem is coming from the equation, Professor Dr. Singh in a Sunday initial lab, he said that if the problem is coming from the equation, why don't we change the equation? That was his original idea. And also he kind of extended how the material points are interacting with each other. So in his new formulation that we call peridynamics or peridynamic theory, he said that all material points actually can interact with each other. So they don't need to touch to each other. And also the way that he defines the interaction is through this something that we call peridynamic forces or bond forces. So this is the force that this point is acting on this, and this is the force is this point is acting on this. And what he basically did is he just rewrite the equation of motion of each material point. Now instead of in terms of a partial differential equation, now we have an integral equation. If you compare these two equations of Cauchy and Dr. Silling's, basically what you see is many of these terms, they are the same, except the problematic term. Now, instead of this term with the derivative, now we have an integration. So basically, this is just saying that, you know, the total forces acting on a particular material point is equal to the density times the acceleration of a particular material point. And as you will see, you know, this equation does not have any derivative. That means that it is always valid regardless of the discontinuities. And you know, as Professor Dempsey mentioned, the original formulation was introduced in 2000, but as the time progresses, actually there are lots of progresses in the theory by itself. And now, depending on the forces material points are acting on each other, we are classifying peridynamic theory in different ways. So if the forces are in arbitrary directions, we call them as non-ordinate state-based theory. And if we make an assumption that these forces that between 2 points, if they are along the interaction direction, but if their magnitude is not the same, we call this as ordinary state-based. And if you go further, if you just assume a pairwise interaction, that means the forces, they are along the bond direction, but also their magnitudes are the same, then we call this as bond-based peridynamic theory. Basically, this is the simplest one, and the original peridynamic theory, although it is simple, it has some limitations. So if you don't want those limitations, basically you need to use these state-based approaches. So now I just want to introduce some basic concepts that we are using. You know, I was just keep talking about the force. You know, I just want to mention how we can calculate that force. But before calculating that force, I just want to introduce an important concept that we are using, which is called horizon. So although a material point can interact with all material points, as you will see, at the end we will do a kind of numerical calculation. So if you take into account all these interactions, it will be computationally very challenging. So, and also, you know, logically, if we think that if two material points, if they are far from each other, the strength of the interaction should be pretty small. So what we can do is we can assume that if outside of a kind of an influence domain or an interaction domain, we can assume that the interaction is zero. So the domain that you can see here is called horizon, and it's a very important parameter in peridynamics. So outside of this region, we assume that there is no interaction. So how about the bond force between 2 points? Basically, this just depending on the material that you are analyzing, but for a linear elastic material, you can think this force is a spring force. But instead of writing this force in a standard way that we are familiar with, like spring constant times the change in distance between 2 points, we are representing this in terms of something that we call bond constant times stretch. So this stretch is basically the change in distance between 2 points after the deformation divided by the original distance between these 2 points. The bond constant is our material constant in this new formulation. But the good thing is we can relate this constant in terms of the parameters of the classical continuum mechanics. So we don't need to do any new experiment. So far, you know, I didn't talk about fracture, but as you will see, this formulation is very suitable to predict fracture, and it's also pretty simple to kind of capture that behavior. Again, depending on the type of fracture that you want to predict, you need to somehow introduce a different criterion. And this is the one that we can use for a simple brittle material. Basically, what you can do is you can always monitor the stretch between 2 points, and whenever that stretch exceeds a certain value, something that we call critical stretch, then we break an interaction, basically, so that these 2 points, they don't talk to each other anymore. So how do we calculate this critical stretch value? Basically, we can calculate based on the fracture toughness of the material. And also, I think 2 talks ago, there was this damage model and so on. Again, we have a similar parameter that we use as a damage parameter. And this parameter is again varies from 0 to 1. So the way that we define this damage parameter is basically the number of broken interactions to the number of original interactions that a material point is interacting with. So just an example, so this is a point now, it is interacting with all points inside this horizon. So there is no damage. So let's assume that after some time there's a crack. So half of the interactions are broken. Now the damage parameter is basically 0.5. So this is a parameter between 0 and 1. So how do we find this relationship, the critical stretch and the fracture toughness or critical energy release rate? Basically, it is coming from the definition of critical energy release rate. So critical energy release rate is basically the energy that we need to provide to the system to create a unit crack surface. So if you can break all the bonds passing to a unit surface, you can determine this relationship. So there is a kind of a logic behind this. So to solve our peridynamic equation, normally it's difficult to solve by using analytical techniques. So we need to use a numerical technique to obtain our solution. And most of the time we are using meshes approach to discretize our domain. So what we are basically doing is we are just discretizing our domain into finite volumes, and we insert a point at the center to represent each volume, so that we can convert our integrals to a summation. And for those of you who are familiar with molecular dynamics also has a very similar equation. But as I said, this is a continuum formulation. And what we basically do is we just calculate the stretch between 2 points at a particular time, and then we calculate the force between 2 points, and then we just find out the acceleration at a particular time. And depending on what you do, either you can use explicit time integration or implicit time integration, then you can calculate the displacement and velocity at the next time step, and you march in time basically. But at the same time, you need to monitor between 2 points, so that if the stretch between 2 points, if they exceed the critical value, then you break the interaction. Now I will just show you some benchmark problems just to show you the capability of this technique. So in this particular case, we have a square plate, and there is this kind of a crack in the middle, and we are just applying a velocity boundary condition at the top and bottom, and this is a pretty high velocity, 20 meters per second. So we are just analyzing a dynamic fracture case to see how this crack will propagate. Before actually allowing the crack to propagate, we look at the shape of the crack, and this is what we obtained. So basically, this is a cusp shape, and if you look at the shape of a crack in actual sense, actually it has this shape as well. So Peridynamics basically capture this shape correctly, and then we just allow the crack to grow, and what we are seeing is basically the crack propagates similarly from left and right, and we can easily calculate the crack velocity as well. And this velocity is basically, for this particular case, lower than the Rayleigh wave speed, which is the upper limit that a crack can grow for this material. So our speed is less than this, so we are in good shape. And then what we did is, for exactly the same geometry, we just changed our velocity from 20 to 50. Okay, exactly the same, so we didn't do anything special, and this is what we observed. Okay, so as I said, for the exactly same model now, we have a much more complicated fracture pattern that we call branching, and this is very common for dynamic fracture. Again, as I said, we didn't do anything special to capture this complicated fracture situation, but Peridynamics can easily capture this. Now another benchmark case, so in this time instead of a crack, we have a hole there, and we just again pull this from top and bottom, but this time it's very slow, so quasi-static case. So this case may look, simpler with respect to the other one. Actually, this is more complicated. Why? Because we don't have any initial crack here. So if you want to use, for example, linear elastic fracture mechanics, you cannot analyze such a problem because you don't have any initial damage in there. So now we would like to see if Peridynamic can also find out the damage initiation. And if you look at here, Peridynamic, since we are pulling at the top and bottom, what we know is basically we should have stress concentrations right there. Again, Peridynamics did a good job in finding out the critical location by itself. So we didn't tell Peridynamics or the simulation to start damage initiation from here, but instead it just does this automatically. And later on, the damage starts propagating to the left and right. And when we show all these results, people are just asking us if we are comparing our results against the experiments. Yes, we are doing. And this is again a very simple material, PMMA, so it's kind of brittle material by itself. And this is something called diagonally loaded square plate test. So what we are basically doing is we are just pulling this specimen from top and bottom, and depending on the crack orientation, mixity changes. So the way that crack propagates is different. So the left-hand side that you can see, they are from experiments, and these are from our simulations. Again, if you compare these, you see that Peridynamics could capture the fracture pattern very accurately. And again, we didn't do anything special to capture these. And as you will see, also Peridynamics is also very similar to impact problems, and there are different ways that we can simulate impact. It's a very simple algorithm that Dr. Sering proposed a long time ago. Basically, what we are doing is we are always checking to see if there is any metal point inside an impactor. So if this is the case, we just say that this should not be the case, so we just move the point outside of the impactor, and this is how we can model contact situation. And this is again a very basic or kind of a benchmark problem for dynamic fracture for impact cases, which is called Kalthoff-Winkler experiment. So we have a kind of an impactor here, we have a kind of a thin plate, steel plate, and we have two cracks here. So normally you may imagine that these cracks, whenever this hits, is supposed to just grow self-similarly, but since it's a dynamic situation, basically it grows with an angle. And this is basically our simulation. So let me just do a small video here. So the impactor is basically hitting from top side, as you can see, and later on we see these crack patterns with a particular angle, and we just compare this crack orientation against the experimental data. As you see, they're almost on top of each other. And so far, the material that I just presented is for an isotopic material, but actually this is a very general formulation, so you can model any type of material, but just to give you an idea, I will briefly also show you how we can model, for example, a composite material. Why? Because it's an anisotropic type of material. Since we have fibers and matrices, so that fiber direction is the strong direction. So whenever you have a new material behavior, so you need to somehow come up with a new material model. So in this particular case, since the fiber direction is a strong direction, what we basically did is we introduced a different bond constant in the fiber direction to make that direction stronger. And again, for all bond constants that we can introduce in Peridynamics can be calculated in terms of the material parameters in classical mechanics. And this is just a simple example. Again, we have a thin plate, we have a crack in there, we just pull from both sides, and we just want to see how the crack propagates. And this time, now we have this effect of fiber orientation. So we just look at three different orientations with 0, 90, and 45. And in each case, what we observed is basically the crack propagates along the fiber direction. Again, if you look at the experimental data, you will see that actually Peridynamics does a very good job in capturing the correct fracture behavior. Now, after this introduction, I just want to also share with you, the some preliminary results that we obtained for ice. And I have another student in my group. Basically, he's looking at also not peridynamic side, but he's just looking at simplified modeling of ice structure interaction and also ice-induced vibration and so on by using advanced MATLAB models. But I just want to emphasize for those of you who are familiar with these. So we are just trying to look at how the ice interaction takes place if we have a one-dimensional model. So as you can see here, depending on the velocity of the ice, we see a different fracture pattern. So what we are seeing is basically if it is slow, so we have this nice pattern of displacement time variation. But if it is if the ice is very fast, so we see this type of pattern. And also, if you look a little bit in more detail, what we are saying is again, if the ice velocity is very small, we see bending type of behavior, and once we start increasing the ice velocity, we see bending crashing behavior, and if the ice is very fast, now the damage pattern or damage mode is basically crashing. So this is what we were trying to basically capture by using peridynamics, and this is one of the actually the first example that we saw in one of the PhD theses. I think it was done at NTNU in Norway, and there is just a kind of a cubic block, and it says let this block to hit the bottom of the structure to see how this thing is basically split apart. And this is, as you can see, once this cube just hits the bottom side, as you see, we have a pretty complex fracture pattern that we can observe, and these are they are all produced by using peridynamics. And then what we did is we just look at this simple experimental setup, and in this particular case, we have a pretty thin layer of ice, and there is this cylindrical structure, and this cylindrical structure is basically hitting the ice with a different velocity. And as I was just trying to show you earlier, depending on the velocity of either ice of the structure, we should observe different behavior, starting from bending to crashing. And as you will see, we start with a very slow velocity, and we were able to capture kind of a bending type of behavior. This is kind of force versus time. And as we keep increasing the velocity of the structure, we start seeing, or we are kind of moving towards the crashing behavior. Basically. So these are just gave us some indication that the tool that we are using can capture it is called qualitatively the right behavior. And then now you can see the damage pattern as we move the structure. You can see that we can capture the damage as we move from here to there. And then we look at this, it was kind of qualitative, so I asked my student to start looking at much more quantitative type of work, so that we can, our predictions can be much more accurate. And we found a paper, and then that paper was talking about the in-plane fracture of an ice flow. So in this particular case, basically we have this square plate, and we have a crack in there, and then we have this in-plane load acting at the crack tip. And basically we want to see if we can capture the size effect which was observed in the experiments, and we look at 4 different scenarios. And for all these scenarios, basically there is also an experimental data that Professor Dempsey generated a long time ago, and we just wanted to see if we can actually capture the correct fracture load when the crack starts to propagate. And as you can see, the experimental data and the data that we generated from Peridynamics, they match pretty well to each other. Again, it gives us a good indication that our tool may be a good fit for ice. It is for in-plane fracture. Now, recently we also look at this ice sloping structure interaction problem. Again, somebody was working on this, and we wanted to also simulate by using Peridynamics. So now, instead of a cylindrical basically impactor, now we have a conical impactor. hitting a kind of a pretty thin ice, and we just want to see, how the fracture is generated. And these are some experimental results that people observe. So once the conical structure hits, basically what they observe is they first see the radial cracks occurring, and then after that they observe this circumferential crack after some time. And somebody again in 2011, they used a simulator to observe this. As you see, first the radial crack starts and then circumferential cracks grow after that. And we were trying to see, if this can be captured by using peridynamics. As you see, once we hit the ice by using this conical impactor, so we were able to capture these radial cracks, and after some time the circumferential actually cracks start to grow. And once we actually continue our simulation, what we are seeing is we also see that the circumferential cracks, they have a tendency to grow as was observed in the experiment. As I mentioned, another kind of goal for us is to look at, to use peridynamics at small scales, not just macro scale, but we want to see also if we can capture things happening at the micro scale. And this is a very simple example. For that, want to see how the macro cracks and micro cracks, they are interacting with each other. And this is where we started. So we have a macro crack there, and we have a micro crack, and we pull this specimen from top and bottom. And as you see, later on, this macro crack just merges with the micro crack, and they both propagate together. And later on, we put two cracks which are parallel to each other. Again, what happens is basically these two guys, they merge each other, and we didn't stop. So we just keep adding multiple micro cracks in here to see, the effect of it. And we didn't stop as well. And finally, we just tried, I don't remember the numbers here, but we have a large number of cracks to show you the capability of peridynamics that, in the beginning I mentioned that, we don't treat cracks as special objects. So we can have as many cracks as we have. Okay, so by using some other techniques, you cannot model such things, okay, because it can cause some numerical issues and so on. So basically, what we are seeing basically here is, now the macro crack just again merges with some of them, and then they propagate together. And the last thing that I want to show you is, as we know, again, ice can have a crystal structure, and if you want to predict cracking at microscopic or crystal level, again, peridynamic can be a good tool for this. And this is not for ice, but soon we will work on it. So this is basically what I will show is for a steel structure, but again, it has a crystalline structure as well. So when we talk about crystal structure, we need to look at or consider different type of crystal systems. And as far as I know, ice has an hexagonal type of crystal structure, but in this particular study, we will just show you the cubic crystalline system. And for cubic crystalline system, this is basically the material matrix that we have. So we have only 3 independent material constants, and this is just a representative of a microstructure with many crystals. And again, whenever you want to model something different than isotopic material, then you need to come up with your own material model, which can be representative of this one, and this is what we obtained, so I don't go into the detail. And basically what I want to show you is, we just look at some fractal patterns that we can capture by using this polycrystalline model. So we just have this square plate, we just pull from left hand, right hand side, and we have this initial crack, but we don't have to, but we just want to see the effect of these initial cracks. And the kind of the thing that we want to see the effect of the strength of grain boundaries. So we want to see if the grain boundary is weak, what happens if it is stronger than the bulk material, what happens, and so on. So if the grain boundary is weak, so whenever you see this parameter smaller than 1, that means our grain boundary is weak. And in here what we did is, we just did a kind of a convergence study to see that if we change our grid size, can we capture consistent fracture patterns. And also we want to also see if you use smaller or larger grains, how it is actually changing the fracture pattern. And later on, once we start decreasing our grid size, what we see is basically the fracture patterns, they start convergent. So that, it can give us an indication of a right grid size that we can use in our simulations. So if the grain boundaries are weak, so what you see is basically you have lots of branching and so on. So the microstructure is very important, but once you have grain boundaries stronger and stronger, then the effect of the microstructure becomes invisible. And as you can see, here we have these initial cracks. So once we have the stronger grain boundaries, these two cracks, they just want to merge each other without paying attention to the effect of microstructure. And also at the same time, we also capture something important at micro scale, which is called micro crack cloud mechanism. So basically, sometimes, especially if your grain boundaries are weak, so depending on the initial crack, basically, and their distance to the grain boundaries, sometimes the cracks may start from the grain boundaries and they can stop the original crack. And this is called micro crack shielding, and this is something that we captured again by using our simulations. And this is just kind of a final plot for me to show that actually, depending on the strength of grain boundaries, we can capture either intergranular type of fracture pattern or intragranular type of fracture pattern in a pretty straightforward manner. So this, since this is a new theory, we want to actually, educate more people throughout the world, and actually the trend is, especially during the recent years, is pretty good. So we wrote this book just to, explain more about the theory, and also, for newcomers to learn more about this theory. And, if you are interested, I can send you the PDF of this book. And as a final remark, now, there is this new technique which looks like, it's very, very promising for predicting fracture. So, and also now we are hoping that it can be sort of a pretty good or promising tool for ice mechanics. So that's what kind of the message that I would like to give. And that's my final slide. And thank you very much for your attention.
Are there any limitations to this method?
So ideally, there is no limitation. As long as the continuum approach is valid, so this approach doesn't have any limitation from that sense. But once we start losing or once we are approaching the atomistic scale, then once the continuum mechanics becomes invalid, then again this approach will be invalid as well. But other than that, it's just up to us, basically. So you can model any type of material and any type of fracture pattern. So if there's any limitation, that's the limitation of us. So if somebody can come up with the right formulation, they will just use it.
So when you create a fracture, you're breaking these interactions. What happens if you then sort of reload a crack, or say you have a shear fault where you've broken interactions, but you have sort of friction on that how would you account for something like that, where you do have some interaction, the crack is fully broken, but you either want to reload it and see how it closes, or?
So basically, again, it just depends on us, depending on the material that we are analyzing. So for the example that I just showed you, we assume that if the bond is broken, it will always be broken. But it is possible that, for a particle material, if there is some type of healing and so on, we can just introduce into the formulation as well. And we can also include friction as well.
Yeah, so maybe you already explained this, but I didn't quite understand if there was, if you could define these forces such that it could match any continuum model.
Mm-hmm.
So there's a well-defined way of doing that matching so that you get exactly a continuum model solution.
Yes. Of course, the logic of peridynamics is very different than classical quantum mechanics. So, ideally, we don't have to make that connection. But since classical quantum mechanics is there for a long amount of time, and since we have all this extensive experimental data and all these material models which are all available, this is the logical thing to make this connection. And it is possible. So you can, if you have a material model in classical quantum mechanics, there is some type of transformer, and it can just translate to the peridynamic world. So you can just take it from classical sense, and then it will convert it to a peridynamic formulation. So that's possible.
So maybe a more specific question. Let's say for just pure linear elasticity, what is the transformation? Is it simple?
Well, it's very simple. It's very simple. As I said, I just mentioned about this our bond constant. Basically, I just said that it can be expressed in terms of Young's modulus, for instance, or elastic modulus. So this is a very simple transformation. And the way that we do it is basically we just imagine a scenario in a way that we can calculate the strain energy of a material point. So if you calculate the strain energy density, let's say from classical quantum mechanics and peridynamics, they should be the same. Once we equate, it gives us the relationship basically. But there is also a much more formalized way of doing or converting your material models in classical quantum mechanics to the peridynamic form.
It's very interesting. I haven't been introduced to this before, so thank you very much. I just wonder, how far these things go. I mean, for instance, like the localization of deformation. Can peridynamics capture the localization of deformation?
So can you a little bit more, expand more about this?
The idea, for instance, I think of like Costin, for instance, when he also said you have that sort of domain around his tracks, and then the alternative formulation, which actually is used, like the Rudnickian Rice formulation of instability, and that gives you a localization of the deformation. So this will sort of give you an incipient crack forming, and then like an earthquake fault, for instance.
So maybe we can actually discuss more about this because I want to learn more about what you are saying. But as I said, this is a very general formulation. So I believe that as long as, or if classical quantum mechanics can capture this, so peridynamics should be able to capture this as well. But I cannot, give now in detail about how we can do this for this particular application.
I do have a couple. I'll start with the first two. In the modeling, right, how does it know between two bonds are separated by a crack? Because you have the horizon, which were based on the distance. So if two points are separated by the crack, how does it detect in your formulation?
So what you are saying is you want to have an initial crack?
No, let's say in general, if two points are separated by a crack, there should be no bond between them.
That's correct.
So in the formulation, how do you tackle that? Because you only have the horizon, which is based on distance. So between one separated by a crack, one without, they should be different, right? Because there's a crack between them. So how does it account for that?
So basically, if you have an initial crack, then what you do is you just initially break all the interactions passing through that crack surface. But if you don't have a crack, initial crack, then as I mentioned, you monitor the stretch between 2 points, and whenever they exceed this critical value, you start breaking them. But breaking one bond doesn't mean that you will create a crack surface. So once the bonds start breaking, that part becomes pretty weak, and then it's a kind of a place that cracks can emerge from that particular place. So more bonds will more bonds will be broken in that particular part, and as a result of this multiple breakage of bonds, you start creating a crack surface in an automatic manner. So we don't kind of guide, we don't just We don't impose anything to the formulation. Everything is happening in an automated fashion.
Yeah.
Very interesting. And I like it, this Lagrangian way of doing it. Can you tell me why it is called Peridynamics?
So basically, that particular word is coming from Greek. So I mentioned about this horizon, which is an important parameter for us to dictate the domain of influence. So the horizon in Greek is peri, and dynamics is source. So that's where it's coming from.
When you,
I'm interested in this formula where you introduce this fracture energy and then get the distance. Can you go back to that slide? I want to look more about this formula.
Is this the one?
Yeah, this is one. This is interesting because I see you have data in this equation.
That's right.
Meaning that if you choose different influence radius, I call it, or cutoff, then you have different S0.
That's correct. That's correct.
And my question is that how sensitive is your result in your choice of data?
Yes. So this horizon is basically something that we can call a length scale parameter, which doesn't exist in classical quantum mechanics. Okay. So, and depending on the problem that you're analyzing, you may have this length scale effect or not, basically. So, if the problem doesn't include any influence of this length scale, then the horizon size should be 0 or very close to 0, so that we should converge to classical quantum mechanics. Okay, but if we converge to 0, then what happens is, then since we are using or doing these numerical simulations, then our discretization should also be very small. So then our computational time will be very, very large or very high. So then what we need to do is we should just choose a suitable horizon size for ourselves. And then what you do is you just try different horizon sizes to see that you will achieve some type of a convergence. And that's what I also showed you for this polycrystalline case. So here, I have different horizon sizes. Sorry. Here. So all these guys, they have a different horizon value. Okay. Actually, we should look at these guys because they have the same grain size. And as you see, once you start using smaller and smaller horizon size, the fracture pattern becomes the same. So whenever you find out that horizon value, which can give you a convergent result, then you can use that horizon size for other type of cases. So you should do first some type of a convergence study.
Is that formula in your book?
Yeah.
Okay, thanks a lot.
I have two questions. First, whether it's possible to have gradient theory in your peridynamics, and the second question, am I right to say that if you do not have experiment, you cannot really tune your result, your computation, you can predict nothing. But on the other hand, the statement is it's always, you can choose two parameters, size of the element, size of the time step, and size of the horizon that fit any possible experiment.
Mm-hmm. So, straight gradient theories are also, they are non-local theories, and if you do certain assumptions, you can make them the same, basically. So in some special case, string gradient theory and peridynamics, you can prove that they are the same. But I believe that peridynamics can be considered as a much more wider domain formulation with respect to string gradient models. And regarding your second question, at the end, of course, we need to use some method parameters, and especially to find out this horizon size, basically, then we need to calibrate, as you are saying. That's correct. If that particular problem include some type of this length scale effect. If not, then it should automatically, once we do this convergence study, we should automatically capture for any size, for any discretization.
Bob?
I did have an original question which has already been addressed, I think, the calibration issue.
Mhm.
But within a body that's experiencing damage, then the scale of things is changing within the body itself. How do you account for the calibration at the finer scales within the, you know where I'm coming from?
So I think in this particular case, whatever we should do in the classical formulation, again, something that we need to somehow come up with new ways of capturing that particular situation. That's what I can answer. So this is not a tool that it can capture everything right away. So basically,
Can you explain a little more about your S0 function?
so basically that.
Can we go to the
Sure.
slide?
Mhm. This is the one or the other slide?
The other one. maybe.
Okay. Mhm.
Yeah. That W0 or and S0, what's the basis of that?
So basically, what we are saying is, as I said, this particular relationship between the critical stretch and the critical energy release rate that I'm showing you is coming from the meaning of critical energy release rate. So if you think about now a unit crack surface, then if you just consider or take into account all bonds passing through that surface, so you need to break all those bonds. So before breakage, then the energy of each bond will be that omega 0. So this is actually an energy of each bond just before the breakage. So you need to break all the bonds passing through that crack surface, and when you sum them up, that value should be equal to the critical energy release rate. So once you put these two together, you obtain this particular relationship. So again, you are trying to represent the definition of critical energy release rate, nothing else.
So I was a little disappointed that we saw like a qualitative comparison.
Mhm.
Suppose you took Broberg's problem, right? 1960, dynamic expansion of a crack from a point.
Mhm.
Not quite the first dynamic solution, but you could have compared your solution with, now, because that's an elastic solution,
Uh-huh.
if you made a comparison, would you get the same solution? Because it's not enough to show qualitative comparisons like that.
No, I also provided some numbers.
You know,
as well.
you've got Elizabeth Yoffe's paper of 1950, which was the first paper to study dynamic fraction.
Uh-huh.
So you showed qualitative stuff.
Mhm.
So then, but if you said, all right, I've got a length scale and I can predict at what the crack velocities will be under these situations as a fraction of the Rayleigh speed, there's an enormous amount of theoretical and experimental work on that. And one would like to know how quantitatively correct you were. But suppose you said, oh, well, I need a length scale. Well, the first dynamic solutions in the lattice were by Leonid Slepyan, and you could go to his lattice solutions and see what your solutions did there. Now that's got a length scale, and you could see what you did exactly. That's what I would have. Is that in the book?
Actually, you can see these type of also quantitative comparisons in many peridynamic works, so they are available.
They're
So
available.
also, although I didn't cover everything in here, although some of the things are, according to me, they are kind of
Because
still.
it's a little surprising to me. Even, you know, when you take that stretch and you drop it, you go to the slide where you make it 1 and 0.
Is this the one that you?
No, you changed your, which was it? when it didn't have a crack, you had to change your stretch, I think.
So in this particular case,
Just go back and I'll see it. I think it's backwards.
Damage parameter. I think you're talking about damage parameter.
Yes, that's it.
Okay.
Back one.
Yes.
One back.
Okay. Yes.
See, when you needed that because you needed to create a break, right?
That's correct.
But when you do that, you drop all the energy. You fail it immediately. So you drop all the energy in the mesh.
No, only for bond. So one bond doesn't mean that you create a crack. So you are just,
But it's
starting a
like-
damage.
What
Think about a
softening?
micro.
A lot of the considerations of the question were coming from
Uh-huh.
materials with softening, so that has no softening. And it's
No, but the thing is, as I mentioned, so this is a very basic definition of a damage. So it doesn't mean that this is the only kind of damage criterion that you should use.
or you've got
Of course, you can use many other things for different materials. This is a very general continuum mechanics formulation. You can model all type of materials. But once you move from one material to another one, then you need to start updating all these criteria, plus the material behavior as well.
Okay, can we go to where you got branching? See, that's a little surprising. You increase the speed, this speed, right? From
That's
50 to
correct.
50. But your cracking speed must have got to that critical fraction of the Rayleigh wave speed to get branching. So that is quite a interesting result. And you know that there's no agreement yet what causes branching.
So there are also some papers actually specifically also analyzing this branching behavior
Like
in depth. Yes, by using paradigm. So I can share those with you.
Further questions? Alex?
Yeah, but very different. It's a kind of methodological question. There are codes based on finite elements with fracture and SPH codes. So how this your code, your theory stands compared with existing?
Sure.
And are you expecting to enter market, or there are no chance to do this, or they just not science but business?
So basically regarding your question is, you are saying there are different type of approaches which are trying to do similar things in both in finite element framework plus SPH and so on. So SPH is, the formulation itself, if you look at the equations, they look similar. But the fundamentals of SPH and Peridynamics is totally different. So SPH is a kind of a purely numerical approach, and this is, as I said, continuum mechanics formulation. But of course, you use numerical techniques to solve our problems. But if you look at other things like cohesive zone and extended finite element and so on, so those approaches are also pretty strong, but they have some limitations in some certain cases, especially if you start moving from 2D to 3D. So from Peridynamic side, I believe that, for example, MSc now is interested in implementing Peridynamics inside this framework, and also LS9, I think, already implemented. But because of I think they are a little bit scared, about the reaction from the people, because they very much use finite element. They don't explicitly say it's Peridynamics, but as far as I know, they implemented in LS9.
Just a simple question. I think I like this theory. In classical elasticity, we try to solve for displacements, stresses, and strains. In your case, what are the objectives? What are the variables you are trying to solve for?
That's correct. So at the end, let's say if you think about, again, classical continuum mechanics, and also let's think about finite element, our first goal is to find out deformations. Again, the same. So we are trying to find out the deformations. But in classical continuum mechanics, the parameters are different. So classical continuum mechanics is using, let's say, stress as one of the parameters to define the state of a material point, or deformation state of a material point. But in our case, we are using these peridynamic forces. So we don't have stress. So we are using different parameters in our formulation. But at the end, we are both using classical continuum mechanics, and we are again imposing Newton's second law for each metal point.
In your macroscopic and microscopic crack interactions, can you show us that slide?
Yeah, you sure?
The macro crack and a bunch of micro cracks.
Yeah.
I'm just wondering what variables you are showing. The color scale. Yeah.
There's damage.
What
What
is
we are seeing is all these colors are damage. Damage plot to see how the crack is propagating. So these are damage plots, which is going from 0 to 1.
Okay, so the cracks. I mean, in general, in classical mechanics, we have a micro crack, we have a smaller crack.
That's correct.
You can, for example, calculate the stress intensity factors.
You can also calculate stress intensity factor here
Yeah.
as well. But here we just want to see the crack propagation. But if you want, as a post-processing step, you can calculate.
You can do all the things.
Yeah, you can do it.
Calculate stresses.
Sorry?
Can you calculate stresses?
Yeah, of course, you can calculate. As I said, normally we don't use stresses, but as a post-processing tool, you can calculate stresses.
How would you define stresses?
So basically, it just depends. So basically, what you can do is you can look at the kind of forces passing through a particular surface of your metal point. You just sum them up. You just divide by the area. It will give you stress, for instance, in a simple manner. But there are some much more formalized ways of expressing the stress definition in terms of peridynamic forces.
I'll talk more maybe later.
That will
Thank
be
you.
I think okay, one more question.
Can you go back to the size effect, the test that you would have shown?
Okay.
We compare this one. We compare the one on top. I suppose is the one that you have for your simulation, and the one below is the one from the experiment.
That's correct.
The simulation, right? Do you calculate the slope that you have at the end?
So we
Because it
just
goes to every FM, which will be negative 0.5. But that slope, do you calculate for the mean value?
So honestly, in this particular case, still these are preliminary results. So we didn't really did the in-depth investigation of this. But it's a good idea to check, if we can capture the same trend as it is observed in the experiments.
Just one very short question. Do you have any comparison between, let's say, for all those fracture tests, you could easily find the load displacement or load versus crack mouth opening displacement? Any of the papers that...
Yeah, they provide all these things, yes. You can find this information.
Well, I think we've also startled. We need a glass of wine.
Thank you.